inverse functions, and there's a bunch of things about inverse functions. One of our most famous pairs of inverse functions is ones we just talked about, exponential functions the other day. Here's an exponential, maybe like e to the x. Do you remember what the inverse function of e to the x is? The natural log of x. This one looks like that. E to the x goes through 1 on the y-axis. Natural log of x goes through 1 on the x-axis. They are reflected across the line y equals x. Okay? That's a quick little synopsis. But we need to remember, how do I know if a function has an inverse? All right? It passes the horizontal line test, right. So note. A function has an inverse if and only if, that's right, it passes, and we'll just put H line test for horizontal line test. Now, by the way, this little term, this little phrase, has an inverse, right here. We can also say that differently. We could say a function is one-to-one. And the reason I say that is because I think maybe your book refers to it that way. Is one-to-one. And, if they ask you, for example, is the function one-to-one, then they're asking you, does it have an inverse? All right? Which means, does it pass the horizontal line test? So let's go back to one of our family members. F of x equals the absolute value of x. So what's the answer? Do you remember what that function looks like? Do you have a visual image in your head? The visual image should look something like this. Yay. Right? So does it pass the horizontal line test? No, it does not. So, no, that one is not one-to-one. How about our old friend, the square root of x? The square root of x. Yes. Is it one-to-one? Does it have an inverse? Yes. Most definitely. It just looks like this. So it passes the horizontal line test because it only hits it once. Now, there is a way for us also to confirm if two functions are inverses. Note, two functions are inverses of each other if, let's say that those two functions that we're checking out are functions f and g. All right? They are inverses of each other if f of g of x is the same thing as g of f of x, and they both are, do you remember what it is? They must simplify to x. If two functions are inverses of each other, then when I plug them into each other, they should simplify to x, to that line of reflection. Okay? So, for example, Let's consider these two. F of x equals x cubed, and g of x equals x to the 1/3 power, which is also like the cube root. All right? If I wanted to see if those two were inverses of each other, I would plug them into each other. So I would do f of g of x, which that means I'm going to plug g into f. So I'm going to have x to the 1/3 cubed. So what is x to the 1/3 cubed? Well, power to a power, we multiply, I get 1, so it's just x. So far, so good. Now let's do g of f of x. So that means I'm going to plug f into g. So I'm going to have x cubed plugged into this function, so it'll be raised to the 1/3 power. Power to a power, that also simplifies to x. All right? Now, you may be asked tonight to graph two functions together, all right, and take a look at them and see what we know about whether they are inverses or not. For example, let's say that they ask you to A, graph together, and then B, graph f of g and g of f. And of course, this is something you could use your graphing calculator for if you wanted to. All right? So let's say that I add this one. Let's just kind of look at one we already mentioned. Because I think we can do this one without even looking at a graphing calculator, hopefully. Now, if they told us to graph these two together, all right, e to the x would go through 1. Here would be e to the x. And the natural log of x would go through 1 on the x-axis. Now, obviously, we already talked about these. These both have an inverse, don't they? And they both appear to be reflected across the line y equals x. They are. Okay, if we were to draw those correctly, they would be reflected across that line. Now, part B, graph f of g and g of f. Okay, this is part A. Part B, well, what is f of g? Now, if you were doing this on your graphing calculator, you would be plugging g into f right here. So I would have e to the natural log of x power. Right? Now, don't we know a little property about that? E to the natural log of a mess is just the mess, right? Isn't this just equal to x? Right? According to that property, and we're going to be reviewing those starting the next day or two. E to the natural log of a mess is the mess. So what if I were to do g of f? What if I were to go the other way? Well, now I am plugging f into g. So I'm going to have the natural log of e to the x. There's another property. The natural log of e to a mess is the mess. This is also x. So when you get ready to graph b, it's just going to be this. y equals x. All right? Even if you had entered them into your calculator like this and like this, that's what it's going to graph, because your calculator knows that that's the case too. All right? Next. What if you're asked to show that the function is 1-to-1? That means show that it has an inverse. And find its inverse. This shouldn't be that bad. So, let's say that my function was negative 2x plus 4. Now, how can I show that that puppy is 1-to-1? Does it pass the horizontal line test? Yes. So let's think of this. What is this function? Well, it is a linear with a negative slope going through 4. So I think, every linear would have an inverse, wouldn't it? Okay. Passes the horizontal line test. So now, how do I find the inverse? Do you remember? I make this a y. Y equals negative 2x plus 4. Then I trade my x and y. So it becomes x equals negative 2y plus 4. And then solve for y. Right? Subtract 4, x minus 4 equals negative 2y. Divide by negative 2, divide by negative 2. There is your inverse function. And I could write it, I guess, a couple ways. I could write it like this, or I could write it as negative 1/2 x plus 2. But we have now found the inverse function. Yeah. Yes, you could also do negative x over 2 plus 2. All right? And we are going to stop there for today, I believe.